All right. Well, let's go ahead and get started. Remember, we are beginning vectors today, but it is not on your exam. So let's just get right to it. The exam is Thursday, yes. Then Friday, we'll go ahead and take it on a case-by-case basis. And Mr. Gonzalez and I have already been talking about the possibility, because everybody's bringing up the possibility that we're supposed to get 1 to 4 inches of snow over the next couple of days. So as of right now, we're just going to go with the normal schedule that we went ahead and set forth, and we'll go ahead and change it as necessary depending on what happens. Okay. All right, so let's talk about some vectors. Yes. See, I don't think it's the amount of snow. I don't think it's the amount of snow. I think it's how bad icy the roads are. Yeah. Okay, let's go ahead and get started. Okay, so the physical world. Okay. Okay, the physical world is filled with applications of vectors. For example, your speedometer represents how fast you're driving. This value is known as a scalar because speed can be defined by its magnitude alone. Now, this word magnitude, we're going to be seeing and hearing it a lot over this unit. Okay, only the value or number is important. Temperature, area, mass, time, they're all examples of scalar quantities. Well, it's just a numerical value. Now, when we're concerned with both direction and magnitude, such as velocity, then we have a quantity called a vector. So see, magnitude can be a lot of different concepts. Yes, ma'am.
Are you going to post the video of vectors?
I will.
Oh, yeah.
The very first day I teach vectors, I always show that clip, but I'll do it at the end.
Can we watch it every day that you teach vectors?
I don't think I'll remember it.
That's okay, I'll show it. I'll show it. Now, in order to have a vector, you have to have magnitude and direction. But as I was saying, magnitude could represent different ideas. For us, primarily over this unit, it's only going to represent 3 ideas. Now, we will see a little more, though. But primarily, it will be speed of an object. It could be the distance traveled, or it could be the weight or mass of an object. Those are going to be our primary magnitudes that we're going to be dealing with. In fact, a lot of the first examples we're going to see today, the magnitude is just the length of the vector itself. So just really easy ideas. Because I can go ahead and say, I'm traveling at 25 miles per hour, but that doesn't mean anything unless you're given a direction. Okay, that's what constitutes a vector. All right. Now, vector applications appear in economics with the velocity of money, vector graphics and computer graphics, and probability vectors in statistics. Okay, so let's take a look at one. A directed line segment, just as we see right here, is the geometric representation of a vector. The starting initial point P, so you always start at point P, we call that the initial. It's the tail or base point, and the terminal point Q, indicated by the arrow, is called the head, tip, or terminal point. So all of these are used interchangeably. Typically, I'll go ahead and refer to these as initial and terminal, or maybe tail and head. Okay. Now, this notation is written as V is equal to PQ. Now, I went ahead and wrote this a little larger because the copy really doesn't do it justice here. You'll notice it looks like an arrow is written above the 2 endpoints, but it's only half of an arrow. See, we don't want to go ahead and confuse anybody by making them think that we're referring to something else. Think back to the good old days of geometry. What if I had an arrow above these points here? That's a ray. There you go. See, a ray starts at one point and goes forever in one direction. So that's not what we're talking about. So that's why we have this notation here, when we only have half the arrow. What's that, sir?
Does that mean it stops? Because the ray would be going with one.
Well, that's true. The ray goes forever, but the vector will stop.
That's based on like after.
Yes. Just also to distinguish between the two notations. Okay. Now, the magnitude or length of vector V is denoted using these 2 bars right here. Now, every time you see those 2 sets of bars, that's telling you we want to find the magnitude of the vector. That could be the length of the vector, it could be the speed, whatever it is the problem happens to be referring to. But as we move through the unit, some people might look at some vectors online, especially if you're wanting some extra problems, or you may even be looking in a textbook. A lot of the times they're going to be giving you different notation. So while we're going to be using the double bars, there's nothing saying that you couldn't be given just a single set of bars. When we're talking about vectors, that still refers to magnitude. So the first thing you might think is absolute value, though. Okay. So if we're talking about vectors, when you see a double bar or a single set of bars, we're talking about the magnitude. Okay. Now, in most textbooks, vectors are represented by boldface lowercase letters, such as U, V, W, A, and B. Those are the most commonplace ones that we use. Okay, so before we go ahead and get into some terminology, let's practice making sure we know the difference between a scalar, just a numerical value, and a vector. So a lot of times through this lesson, I'm going to have an additional slide that's not part of the notes that you were provided. So if you want to copy these down, you can. If you just want to follow along, that's perfect too. State whether each quantity described is a vector quantity or a scalar quantity. So let's do the first two together. A boat traveling at 15 miles per hour. That's a scalar. See, we have a magnitude this time in speed, but we don't have a what? We need a direction for the boat to be traveling. That's just a scalar. What about a hiker walking 25 paces due west? That's a vector. So here the magnitude is the distance the gentleman walked, but more importantly, we have a direction. So that's a vector. Silas.
You gotta dress up in the orange jumpsuit on the day of our test.
You know, you're not the first person today to say that.
We were not original, Silas.
If you want to be original, you do it yourself.
Will you come tomorrow in an orange jumpsuit?
Well, I'll do it the day of the vector test.
You will look like you just.
Okay.
You have to get a little vector fixed too.
All right, we'll see. I'll remember that. So now, here's what I want you to do. Take about 30 seconds. Don't say the answers out loud. Try to think about the remaining examples. Would you classify it as a scalar or a vector? Okay, so take about 30 seconds, but again, please don't say it out loud. A parachutist? Oh. Okay, so let's try this first one together, and then I'll start calling on some folks. So a person's weight on the bathroom scale.
Scalar.
Okay, so that is a vector. There you go. Acceleration due to gravity is a vector. So you do have a direction based on the force. Your magnitude is weight this time. There we go. So see, some of these can be a little tricky.
Gotcha.
Okay, let's go to Amna. What about a car traveling 60 miles per hour, 15 degrees east of south? That's a vector. So we have a magnitude and speed, and we do have a direction. Now, you may not be familiar with this type of direction, but after this initial lesson, Mr. Gonzalez is going to go ahead and speak with you about like true bearing, quadrant bearing, and things of that nature. So hopefully you'll be a little more familiar with that. Okay, a parachutist falling straight down at 12.5 miles per hour. Bryn, what would you say? That's a vector. Okay, so we have a direction, and again, my magnitude is in speed. Okay. And this last one here, a child pulling a sled with a force of 40 newtons. Kushal, what do you think? Okay, that is not a vector. That one's a scalar. Now, what do we have here? Do we have direction or magnitude? We have magnitude, it's measured in force, but we don't have what? We don't have the direction that the child's pulling the
It
sled.
has to be both direction and magnitude.
So you have to have direction and magnitude. Downward pull due to gravity. Acceleration due to gravity is a vector. Okay. All right. Oh, I don't think I did this. Now we got some more terminology here. Two non-zero vectors, u and v, are called parallel if the lines through the vectors are parallel. So that just means the two vectors are always equal distance from each other. But here's what's interesting. Parallel vectors can point in the same or opposite directions. So they can still be considered parallel if they're in the same direction or if they're pointing in the exact opposite. A vector that is moved parallel to itself without changing its length or direction is a translation. A translated vector has the same magnitude and direction, but different base points. So imagine this vector up here, if I actually could interact with it, if I could just take it and kind of slide it across my grid here, you'll notice the direction remains the same, the magnitude remains the same, it's just in a different location. That's what we refer to as a translation. The two vectors would still be equivalent to each other. So a vector with its initial point at the origin is said to be in standard position. Okay, so up until now, every time we hear standard position, you're probably thinking about rotating from the positive x-axis.
Yes.
When we're talking about vectors, though, standard position means that the initial point is going to be at the origin. Okay, because it's really, really simple to work with vectors if they're starting at the origin, and you'll start to see that as we get through some examples. Every vector can be translated so that its tail is at the origin. Okay, got a little more terminology here. The term scalar is another word for real number. The product of a vector v and a scalar k is the vector that is k times as long as v. When the scalar is positive, then the vector, product kv has the same direction as v. However, if the scalar is negative, then the vector kv has the opposite direction of the original vector. Okay, so let's put this into practice. Example 1, given vector v. So let's go ahead and say the vector v is 2 units long. Sketch each scalar product using the grid at right to represent each new vector. Okay, so what should I expect to see for 2v? It should be 4 units. What I'm doing is taking the original magnitude, the length, and I'm doubling it. Okay, but it's going to have the same direction. So it's probably going to look something like this. Okay, now remember, I'm also sketching this, freehand, so they are meant to be parallel to each other. It might be a little off, and that's okay. What's going to happen with negative 2v? There you go. It's doubling the magnitude of the original, just like we saw, but the negative changes its direction. So it's going to be pointing downward. Probably going to look something like that. Remember, the negative will change the direction of your vector. Okay, what about 3/2 v? That'll be 3 units long. Okay, but it's still going to be pointing in the same direction because 3/2 is positive. So let's say right there. How many units long will negative 1/2 v look like? 2 units? Just 1. Hey, all in. If you'll put that in the tray, please, sir. And because it's negative, it's going to be pointing in the opposite direction. So let's say I go ahead and draw it like this. Now, think about what we said a moment ago. You remember I was talking about a translation? There's several different ways that I could have drawn negative 1/2 v. I chose to put it in the upper portion here, but there's nothing saying that I couldn't have drawn it down there. You'll notice I just slid it across the screen. It still has the exact same direction, the same length. So the translations are always going to be equivalent to each other. Okay, I could have put it anywhere I'd like. Any questions on that? Okay. Well, let's move on to the next part. Component form. Okay, so if v is a vector in the plane whose initial point is the origin, and what is that? What do we call that where the initial point's at the origin? 2 words? That's standard position now. Standard position, it starts at the origin. And whose terminal point, AB, okay, then the component form of v is given by this. Now, the component form is going to look and act just like a coordinate. But a coordinate just represents a point in space. So the value of A, that's your horizontal distance, so it moves you left or right, depending on sign. B is the vertical distance, so it moves you up and down, depending on sign. But we know we're dealing with a vector because instead of parentheses, we have those arrows on either side. Now, there's a lot we can do with component form. For today, it's just going to be a set of directions. Okay, the component form will tell me exactly how to get from the tail, the initial point of a vector, to the head, the terminal point of a vector. Okay, and you'll see that in just a second. The coordinates A and B are called components of V. If both the initial point and the terminal point lies at the origin, then the vector V is called the 0 vector and is denoted by 0, 0. Okay, well, let's go back into geometry a little bit. If point P located at x1, y1 and point Q located at x2, y2 are the initial and terminal points of vector V, and see we also named it using the endpoints, PQ, then by the distance formula, it can be shown that the magnitude of V is this. How many people remember from good old geometry the distance formula? Okay, we don't remember the distance formula. Some do, some don't. Kind of. Now, all of this is going to be relating back to right triangles. We're still going to be using right triangles, and you'll see how that plays out in just a second. Now, what does this notation mean right here if I have the double bars? Remember, that's magnitude. Now, I'm always going to go ahead and try to use the double bars, but that doesn't mean that if you're given the single bars, we don't want to still recognize that as magnitude. Either of those notations are acceptable. Okay. Now, while we have a couple of different formulas here to go ahead and find the magnitude or length that we're talking about, this is the one that I would recommend you use. I just went ahead and tried to simplify the whole process. Because if your component form is going to look like this, where you have values of a and b, well, then to find the magnitude, you'll simply take the square root of a squared plus b squared. Okay, so let's put all this into a problem. Let's see what it means. Okay, so let me come on down here. Here we go. Example 2. Given the vector v, okay, also named by its endpoints a, b, where a is 3, 7 and b is equal to 6, 5. Now, order is going to be really important here. You'll notice because the a is written first, that has to mean that it's the initial, b would have to be the terminal. If I'm given the endpoints and I want to figure out what the component form is, you always take the terminal values and subtract the initial values. It's always going to be the terminal minus the initial. Okay, so for part A, write the component form of vector AB. So here's vector AB. I'm going to go ahead and set up my component form. So I'm going to start with the terminal, subtract the initial. Remember, it's always the difference of the x's and then the difference of the y's. So I'm going to take the terminal x, and I'm going to subtract the initial x. I'm going to take the terminal y, and I'm going to subtract the initial y. So what should that result in? 3, -2. That's the component form of this vector AB. Here's the A value, here's the B value. Okay, remember, it's not a coordinate, but it's going to act just like a coordinate. Because the first value A is horizontal, I know that I would move horizontally to the right. The B is vertical because it's negative, I know that I would go down. Okay, so let me go ahead and show you this. We don't have to graph this until part C, but let's go ahead and plot these points. Part A was at 3, 7. Okay, so 3, 7 brought here. Then we had point B at 6, 5. Oops, went up a little too high. Okay, 6, 5 right here. So this is B, that's the head of the vector. So here's the vector we're talking about right here. Okay, now remember what I described a second ago, component form will tell you how to get from the initial to the terminal point. Okay, so I'm starting here at the initial. Oh, I'm sorry, sir. You were just on your way in. Okay, so look at my component form. We already said we're going to go 3 to the right because it's positive, 2 down because it's negative. So let's apply those directions here. From the initial point, 1, 2, 3 to the right, 1, 2 down, see we're at the head. That's what the component form is doing for us right now. It tells us how to move from the initial point to the terminal point. And there's a lot more we're going to be able to do with this. We just haven't gotten there yet. Okay. Any questions on how to find the terminal point? Or excuse me, the component form. Okay, well, let's try part B. Find the magnitude of AB. So what's the notation for magnitude? The 2 bars. There we go, the double bars. Okay. Now, there are a variety of formulas you can go ahead and use, including the distance formula, but I'm just going to use the square root of a squared plus b squared. So the square root, what's the value of a? 3, so 3 squared, plus b squared, so that's -2 squared. So somebody simplify that for me. That would be the square root of what? 13, yeah, 9 plus 4. Now remember, if it can be simplified, we want to go ahead and do so, but 13 is a prime number, so that would be the magnitude. Remember, in this case, magnitude means the length of the vector. Okay. Now, you remember how I said a few moments ago that all this was related back to right triangles? Well, let me show you why we have the formula that we do. Let's go ahead and go from the initial to the terminal again, but let's go ahead and actually draw the sides. See how I have a distance of 3 and then the 2? It forms a what? A right triangle where the vector is the hypotenuse. Okay, so hopefully we're able to see now why this formula is making a little more sense. Oh yeah. Okay, now for part C, sketch the vector AB and the translated vector V. So all they want you to do here is put it in standard position. What does that mean? That means the initial point is now where? At the origin. Okay. Now, I don't want to go ahead and call this point A anymore because it's at a completely different location, but let's go ahead, you can call it A prime, that's perfect. Let's go ahead and use the component form to make sure we have the exact vector. So 1, 2, 3 to the right, 2 down. So this should be the head. There's the translated vector. See, all I've done essentially is just slide it across my grid, same direction, same magnitude. They're both equivalent to each other. Okay. How are we doing?
Now do we have to find that angle?
Now, we will be doing that eventually. We'll be finding the direction angle. Yes. Oh, it's just the way the question is asked. You're going to become accustomed to figuring out, what the question is wanting in certain ways. I know that seems kind of strange right now. We'll get there. We'll get there. Okay. All right. Now, like I said, I have additional slides that are going to help us out with these ideas. So let's say I have 3 vectors here, u, v, and w. I'm looking for the component form of all 3 of them. All right, but before we get there, you'll notice only 2 of these are in standard position. Which one is not?
U.
Okay, so everybody's unanimously saying u, but what am I talking about? We did. What has to be at the origin if it's in standard position? The initial point, the tail. There we go, exactly. So the only one whose tail, initial point, is not at the origin is vector u right here. Here's the initial, here's the terminal. Okay, so let's go ahead and start with vector u. I want to be able to move horizontally and vertically from the tail, the initial point, to the head, the terminal point. So what direction am I moving horizontally, left or right? Right, so it'd be positive. So let's see, 1, 2, 3, 4, 5, 6. And now I got to go up how far? So what would be the component form of u? 6, 2. That's it. That's all there is to it. Okay. So let's kind of go around the room here. How about Zeke? I haven't talked to you in a while. What would the component form for V look like? You're very close. 5, 0. So I'm wanting to go from this initial to this terminal. So first we move horizontally. So from here I'm going to go 1, 2, 3, 4, 5. And because we're not moving vertically, that's why I have the 0 there. What kind of vector would I have if it was 0, 5? It'd be straight up and down. Okay, it'd be a vertical vector. Okay. And let's see who I haven't talked to. Hey, Alex, what would you say is the component form for W?
0, -2.
Okay, close. So here's my initial, and I want to go to this terminal. So I want to go from this point to this point. So how far left am I moving?
-2.
Okay, so negative because I moved left, and then how far down?
5.
Oh, close.
-5.
-4. Okay. All right. Questions? Are we doing all right? Oh, yeah, that's not applying here. That's something completely different. Okay. Now, as part of some of our formulas, we will be using some of the trig ideas. That's how we do it. Now, what if I asked you to do this? What if I gave you a question and all it said was this? What am I asking you to do? I want you to find the magnitude of vector u. In this case, we're talking about the length. So remember, when we have it in component form, this formula, the square root of a squared plus b squared, is what we want to use. Okay, so what is a? 6, so 6 squared, plus b is 2, so that would be 2 squared. So this is the square root of 40. Now, unlike the previous one we saw, the square root of 13, this one can simplify. Campbell, can you tell me what that would be? What would the square root of 40 become? Two root 10. Because I could rewrite 40 as 4 times 10. 4 is the largest perfect square that will evenly divide it. Okay, now remember, this formula is based on the Pythagorean theorem. If I come back over here and look at u, Remember, we had to travel horizontally 6 units. We went up 2. See, there's your right triangle. The vector is going to be your hypotenuse. Okay, how are we doing? Is this a review of what you've done? Who are my physics students? Okay, so is this coming back?
We already learned that, like,
So this is all just review, right? This is all new. Okay, all right.
I was like half awake.
Halfway when you did that. Okay. All right. Well, let me go ahead and show you this. This right here is one of my most favorite things to teach in this lesson. Okay. Let's start talking about vector addition. Now, when adding 2 vectors, we draw them using the tip-to-tail method. The sum, u plus v, is called the resultant vector. So whatever operation we go ahead and perform on the vectors, we're going to get our answer, a result. We call it the resultant. Okay. Now, to geometrically represent the resultant, you want the initial point tail of one vector to coincide with the terminal point head of the other. So let me go ahead and explain what's happening here. If you're going to do this graphically, we're going to use what's called the triangle method. There is such a thing as the parallelogram method. I'm not too worried about that right now. If anybody wants me to show them that at some point, I will, but we're just going to go ahead and go with the triangle method. So we're going to be creating triangles based on the operations that we see here. But when we connect these, you can only connect the head of a vector to the tail of another vector. You can't connect 2 tails. You can't connect 2 heads. Okay, it has to be head to a tail. So let's keep that in mind. Let's go ahead and take a look at part A. It says sketch A plus B. Now let me go ahead and run over here to my mouse. It's going to be easier for me to do it this way. Now you'll notice I've created copies of each of these 2 vectors here, A and B. So, see, they have the same magnitude and the same direction. Would everybody agree? Okay, same thing for B right here. Okay, so let's go ahead and show A plus B. So it doesn't matter where in your grid you go ahead and place these vectors. Let's say I'm going to start with A. So let's say I want to put A right here. So this is the head. Okay, this is vector A. Now remember, when you're using the triangle method, you can only connect the head of one vector to the tail of another. Never 2 tails, never 2 heads. So now I'm going to go ahead and bring over B, but I'm going to place its tail at the head of A. Okay. So here's B. Now, the reason why we call this the triangle method is because these 2 vectors are creating 2 sides of a triangle. As soon as I use these 2 sides to finish the triangle itself, when I draw the 3rd side, that's my answer, that's the resultant. Okay, so in this case right here, the vector that I just drew, that represents A plus B. Okay. Now, can anybody tell me what the component form of that vector A plus B is? Okay, what is it? Remember, I want to go from this initial to this terminal. So how far horizontally and vertically am I moving? Okay, so 7 horizontally and 4 up. So say if I'm starting here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. No, that's 4. Anthony. Well, now we're talking about the resultant. When you're first creating the triangle, it can only be head to tail. So when you go ahead and draw the resultant, yeah, there's no way to get past that. You're going to go ahead and have those together. But when you initially create it, yeah, I see what you're talking about. Okay. Now, there might be somebody out there who's thinking, see, I put the head of A to the tail of B. Could I reverse that? Could I put the head of B to the tail of A? Okay, well, let's see. Let's see what happens. Let me go ahead and get those out of there.
it'd be 2 negatives.
Okay, well, let's take a look. Okay, so let me go ahead and move this out of the way. Okay, so I'm going to go ahead and start with B. Okay, let's say I go ahead and move B right here. Okay.
Please excuse my ignorance.
Oh, what am I doing? I'm not going to give myself enough room if I put it there. Let's move it over here. There we go. Okay. So here's B right here. So see, I haven't changed its direction or magnitude. I'm just changing how I'm connecting them. I'm now going to put the head of B to the tail of A. Okay, so just like that. Not tip to tip, not tail to tail. There you go. Okay, so right here, these two vectors create two sides of your triangle. When you draw the third side, that's your answer that we call the resultant. So this right here is A plus B. Okay, but what I want you to do, tell me what the component form is. It's still 7, 4. So the order doesn't matter. See, if I start here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. See, it still works out the exact same. Okay. All right. Okay, let's try another one. Now, for B, when it says sketch A minus B, don't think of it in terms of subtraction. Think of subtraction in terms of adding the opposite. So let's show A plus negative B. Remember, this is one of the first things we talked about in the lesson. If I multiply a vector by a negative, what happens to it? It changes in the exact opposite direction. Okay, so let's start with A. Okay. All right, so I'm going to go ahead and start with A right here. Let's say right here ought to do it. Okay, I'm going to go ahead and draw. Here's the head. So this is A. Now, right now, as it is, B is pointing to the right, but I want negative B. So it's going to be pointing to what direction? It's going to be pointing to the left. That means this right here is going to be the tail now. So I'm going to put the tail right there to the head of A. Let me go ahead and draw in the head. Here's negative B. Okay, this is what we call the triangle method. These two vectors create two sides of a triangle. When I draw the third side, what do we call that? That's my answer, the result we get, hence why we call it the resultant. Okay, so here we go, right there. So this right here would be A minus B. Okay. Now, what's the component form of A minus B? There you go. I want to go from this initial to this terminal. So yeah, I got to go 1 to the left, 1, 2, 3, 4 up. Now, we're going to be doing this graphically today. Tomorrow, the first thing we do when we come in, I'm going to show you how to do it algebraically. So I'm going to come back and look over some of these problems again. Okay, are we ready to try one on our own? Let's try C. 2A plus B. Okay, so 2A plus B. So what I want you to do at the end is go ahead and make sure to write out the component form for 2A plus B, the resultant. Actually, we don't need it right now. We're almost done. Yeah. Okay, so 2A plus B. Let me go ahead and get this set up. Got my component form ready. Remember, the component form tells you how to go from the initial point to the terminal point. Okay, so the only thing that's changing here is vector A, you're doubling its what? Its length. What's another word for length? Magnitude. Okay, so we're doubling the magnitude. Vector B remains the same. Okay, is everybody about ready?
Why do we use the, well, greater than equal sign for this? Is that just to point out to...
Oh, that's just the notation we say that we're using specifically vectors. Okay. All right, is everybody ready? How many people think they have an answer? Okay, so I see several hands going up. Okay, let's see if we're all on the same page. Your component form for 2A plus B should be 10, 8. How many people got that right? Now, see, now there's suddenly more hands raising than a moment ago when I asked how many people have an answer. Okay, let's go ahead and double check that in case you didn't raise your hand. Okay, so the first thing I'm going to do is double vector A. So I'm going to go ahead and I'm going to start over here on the very left side just to make sure I have enough room. So here's one vector A with its normal magnitude. Then I'm just going to take another vector identical and I'm just going to put them end to end. So this right here, this is 2A. Okay, here's the head of that. Now remember, when you're doing this graphically, you can only connect a head to a tail. Never two heads, never two tails. So now let's grab a B. It's saying exactly the same, so I'm going to connect them appropriately. Okay, here we go like that. There's B. Okay, remember we refer to this as the triangle method. Here's two sides of the triangle. Drawing the third, that's my resultant. Okay, so here is the initial, excuse me. Here's the terminal. This vector that I just drew, that's 2A plus B. Okay. Now, starting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Questions? How we doing? Excuse me. Well, the only other thing I want to show you, well, we are going to go ahead and start with this tomorrow. I do want to go ahead and at least show you the properties here. If you have the component form of two vectors, V and W, if you want to add two vectors, well, then you simply add the x's, add the y's. If you want to subtract two vectors, you subtract the x's, subtract the y's. If you want to multiply the vector by a scalar, you just distribute that scalar to each part, both the horizontal and the vertical. And then if I have a vector that I'm going to add to 0, that's equivalent to 0 plus the vector, well, that's just the vector itself. Okay. So these rules are going to make a little more sense tomorrow once I start showing you the examples. But unless anybody has any questions, that's it. Okay. Let me go ahead and stop this.